Yo, 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 what is Gucci, everybody? It's your boy J Siegs with another video on CCT. Today we're going to be talking about the trailing zero problem. A very difficult problem in my opinion, very mathy, very theory, yet it's rated as an easy problem on LeetCode. Okay, I literally think LeetCode makes its problems difficulty based on how many lines of code there are. And let's be clear. Just because you don't have a lot of lines of code does not in any way mean that the problem is easy. Okay? This is hard. So for all you math nerds, you're gonna love this, okay?
Nobody's watching your video.
So, this is going to be it's like I kind of thought about this video before I made it. I didn't write down any notes, but to make things more fun, I'm gonna talk in a British accent. Right, so let's get right into it. If I start sounding like an Australian, that's okay too. So what we have in the trailing zero problem is we're given n, and we want to see how many trailing zeros there are when you compute n factorial. So n factorial is just, as you all should probably know by now, n times n minus 1 times n minus 2 ... you know, until we get to 1. Okay, so yeah, part of the complexity of this is you can't just compute n factorial and then just keep dividing by 0 as long as your mod 10 equals 0. Like you can't just compute this and then say, okay, if this equals 0, then like n divide equal 10 and like count plus plus. And you can't do that because you can't just calculate that, because n factorial is honestly an enormous number. Okay, it's enormous, and it's way, even if you start off with a relatively small number like 20 or 30 or something, the 30 factorial is way bigger than the max int. It's not gonna work. Okay, even log, you know, once you get up to 40, you're done, and you need to be able to handle any number. Okay, so one of my first thoughts was to take it step by step. So what I did was I had a for loop like this, and I feel like I'm overdoing this British accent. I need to tone it down, you know? Okay, so yeah, we have like a little for loop. I guess we should start this at 1, to be honest. I plus plus, and what I was doing is I had a factorial here, but every time I could take out a 0. So then what I did was I did like fact times equals, well, actually hold up, I did it the other way, to be honest. To make this a complete thing, I did it this way, where it starts off at n, and then it's greater than 0 and like I minus minus. And so I multiplied it by n, and then here I did this thing. I did this, and I thought that would reduce it enough. I thought it would take off all the zeros. So what this does is it takes off all the zeros at the beginning as soon as it has any, and then just continue. So I thought I would be able, if I had a big number like this, to just cut off the zeros, and then this number would be small enough than the max int. And that didn't, and like, by the way, you could do this because if a number has a lot of zeros in it, and you're going to be multiplying it by all of these, you will always have at least this many zeros, right? Because when you multiply stuff like this, you will always get in the first 3 spots, if you do your multiplication, 3 zeros and perhaps more, you know? So this was so that's why you can do that, but you can't really do it because again you're going to go over the int max.
Josh, it's called the prologue, FYI.
So my next thought was maybe this part I could cut off and just focus on these front numbers. So, but that didn't even work. So, okay, let me explain. If you have a large number like this and you are doing computing 31 factorial, and like by the time you get here, your number's already this enormous, and you have to multiply it by this number here. So it's just like a small number. Maybe it's like 25 now. So the only numbers that truly matter are, now correct me if I'm wrong.
How?
Emily?
Yeah?
I'm looking at nice places in LA. Why don't you stay in Universal Studios?
Is the first couple things. These integers, these digits don't really matter. They don't matter. So because the zeros are gonna be computed here, like maybe that's a 0 and that gets to be, or that's a 0 and blah 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 blah. Wait, that's a lie. Is that a lie? Let me think about that. Is it possible to get all zeros? Is it possible to get all zeros here? Huh, indeed. Indeed, it might be possible. Okay, fuck that, forget that, forget that. Hi, Stephanie. You have something to say?
I like it.
You like my British accent?
Yes, I like it all.
Okay, so now we're going to be continuing with the most mathy part of this video, when we talk about the number theory, a brilliant solution that I did not think of, and I will not take credit for it because this is so brilliant, such a good use of number theory. Okay, let's get to it. So if we have a number, let's say 26 or something, and we're computing 26 factorial and seeing how many zeros it has. One thing you must understand is one thing you could do. Well, okay, let me say it like this. If you could find all the factors, all the numbers that are divisible by 5. No, okay, how do I want to say this? Okay, okay, let's do it like this. So if we have 26 times 25 times ... times 1. One way you could do it is you could possibly, let's just put the 20 in here and the 10 in here. You could look for all the ones that are divisible by 10 and then just count them. But it's possible that some of the factors, we need to factor these things. So this is 2 and 13. This is 5 and 5. And despite this not being divisible by 10, it is divisible by 5, and this guy is divisible by 2, so we can make 10. Okay, fact. The only way to make a multiple of 10 is if you could divide by 5 and 2.
Did you just do a circle? Yes, because I want the big computer. Pull that. No, just do this.
It's 5 and 2. So whatever we could find of 5, one of these divisible by 5, 5, and a 2 somewhere else, we can make 10. By breaking it up like this, we don't have to look for one of these exactly to be divisible by 10 because we can make that 10 by finding a 5 and 2 pair. Second fact, fact number 2. Fact number 2 is...
Looks nice clothes.
Stephanie, what's fact number 2? Stephanie, can you do word of the day?
1 plus 1 is 2.
Okay. The second fact of the day is escape.
She's like, can I have a word of the day? Your mom's like, 1 plus 1
Second
is
fact
2.
of the day. Prime, if you have two numbers, x and y, and neither of them are divisible by 5, is it possible for their product to be divisible by 5? And if the answer is, and the answer is no, because 5 is prime. You see, x could be split up into its prime factorizations. Maybe it's 2, 3, and 7. And so can y. Okay? Which is 2, 2, and 3. Okay? But if neither of these are divisible by a prime number, their product, which is just can be expressed as the prime, as the product of these prime numbers here, is also obviously not divisible by 5, okay? It's divisible by only these prime numbers. Fascinating. Absolutely fascinating. So what does that mean? What does that mean? Well, we don't have to worry about after we get our 5s from here, or maybe a 5 and 4 from here, we don't have to worry about creating another 5 somehow by multiplying these two. Okay, like there can't be a 5 baby here from multiplying these two if neither of them had a 5. Or there can't be an additional 5 if one of them had a 5. Okay? That was a little confusing of an explanation, but bear with me. So it makes sense to me. And just think about that for a minute. And the reason why that's important is because now when we compute this, in order to find all the 5s that could be factored out of this, all we need to do is find all the 5s that come out of here. And so on. And why all... Okay, and then we also need to find all the 2s that can be divided in all of them. And then we take the minimum of those. And that is going to get us our answer. Right? We take the minimum of the 5s and 2s, because if we have more 2s than 5s, then we could have at most the amount of 10s of the 5s, right? Because if we have a bag of 2 and a bag of 5s here, and we need one of each to make a 10, well, we could only make the amount of 10s that are in the smaller bag, so we take the minimums. More to come on that later. So let's think here. So how can we get all the 5s out of all those numbers? Well,
Actually, still on an accent.
I'm going the whole way, Emily. A mile. That's the British version of Emily.
A mile.
So what we could do is we could find all the numbers in 26 factorial that are divisible by 5, or we could find the amount of them by just counting by 5. So we got, I don't think we're going to count 0. So we'll count 5, 10, 15, 20, 25. However, we also have to divide by, so that's all of them that are divisible by 5. But then we have to see how many of these are divisible by 5 squared, 25. So that would only be 25. So basically we add all of them. So what we could do is we could see how many are divisible by 5. Okay, got that. Then we see how many are divisible by 25, and we just add an additional 1 for each of them. It's not like we find one that's divisible by 25 and we say, oh, that has 2 5s, so we add 2. No, because we already added one of those 5s for this, for being divisible by 5. And let's say we find a couple that are divisible by 5 cubed. Okay? Then what we do is we are able to just count an extra one, right? Because it was divisible here by 5 squared and then divisible by 5. Fact, if you are divisible by 5 cubed, you are divisible by 5 squared. Fact, if you're divisible by 5 squared, you're divisible by 5. Okay, great. So, let's move on, shall we? So basically what we're doing is we have this huge n, let's say enormous n number, and we are computing its fucking factorial. That is so big. Okay, so we have this huge list of numbers and we're counting all the things that are divisible by 5. So we got 5, 10, 15, 20, 25, 30, 35, 4, Then we got 25 here for this is divisible by 5 to the first 5 squared. And then we got all these 5 cubed. And it's going to get less and less and less. Eventually, we are going to look like a pyramid that is exponentially decreasing. Kind of like this. Now we're going to do the same thing for the 2's. We're going to line up all of the numbers here and count all the ones that are divisible by 2. And it's worth noting, this is a fact actually, there will always be more factors of 2 than the 5 when we're taking the factorial. Because it's just because there's a smaller distance between each of these numbers. There's smaller distances. So there's going to be inherently less. There's going to be less distance, which makes there be more factors of them. So back to our bag here. Since it's always true there's going to be more 2's than 5's, we really only have to calculate how many 5's we could find in all of the n's. So in all of n and n minus 1 and n minus 2, we're just finding all the 5's here. Okay, so what's the strategy? So we could have a for loop, and we could start it at 5, and I'll just say I is less than or equal to n, and then I times equals 5. And what we are seeing is we are counting to see how many numbers are divisible by 5 from 0 to n. All we have to do is n divided by 5. So let's have a count plus equal that. And let's make this I too. Now we multiply it by 5. We multiply I by 5 and see how many are divisible by 25. And those, for each one of those, we're going to add an additional one. And this is how we do it. This is how count represents how many 5's we could find, which also means how many 10's there are, which also means how many trailing zeros there are. Okay, let's let that digest. Hopefully that was informative, and hopefully you enjoyed my British accent. Well, that's all we got for today, guys. I hope you enjoyed the video. This was hopefully relaxing and informative. Make sure you.
I hope you enjoyed Josh's brother doing that whole podcast.
Yeah, that was my cousin from Britain. He's from Britain. That's Johnny Boy. All right, this is JC signing out. See you next time.